Let us solve OpenStax University Physics, Volume 1, Chapter 7, Problem 34. A sled and passenger with a total mass of 43 kilograms are pulled 14 meters across snow. The kinetic friction coefficient is 0.23. The pulling force is directed 25 degrees above the horizontal, and the sled moves at constant velocity. We need the work done by the applied force, by friction, and by all forces combined. Work is the dot product of force with displacement. Force times distance times the cosine of the angle between them. But neither the applied force nor the friction force is given. So the first task is not a work calculation. It is a force analysis. Once we determine the forces, the work calculations will be straightforward. Treat the sled and passenger as one object. 4 external forces act on this system. Gravity points down. The snow exerts an upward normal force. The applied force points 25 degrees above horizontal, and kinetic friction points opposite the motion. The phrase constant velocity is crucial. The acceleration is 0, so the net force is 0 in both coordinate directions. Choose horizontal and vertical axes. Only the applied force needs to be split into components. Its horizontal component is applied force times cosine theta. Its vertical component is applied force times sine theta. Always get those from the actual triangle, rather than memorizing which trigonometric function belongs to x or y. Because acceleration is 0, Newton's second law becomes 2 force balance equations. In the horizontal direction, the applied component balances friction. In the vertical direction, the normal force and the upward applied component balance gravity. Friction supplies a third relationship. Kinetic friction equals mu k times the normal force. We now have 3 unknown forces and 3 equations, so the system can be solved. Since the problem asks for the work of friction, keep friction as the remaining unknown. From the horizontal equation, the applied force equals friction divided by cosine theta. From the friction relation, the normal force equals friction divided by mu k. Substitute both expressions into the vertical force equation. This leaves one equation containing only the friction force. The sine over cosine ratio becomes tangent theta. Factor out the friction force, then divide to isolate it. The result is mg divided by tangent theta plus 1 over mu k. Substituting 43 kilograms, 9.8 meters per second squared, 25 degrees, and 0.23 gives a friction magnitude of about 87.5 newtons. The upward pull reduces the normal force, so it also reduces the friction. Friction points directly opposite the displacement, so the angle between the vectors is 180 degrees. Its cosine is -1. Therefore, the work of friction is minus Fk times the distance. Using 87.5 newtons and 14 meters gives -1225 joules. The negative sign means friction removes mechanical energy from the sled. For the applied force, the displacement is horizontal, so include the cosine of 25 degrees. Equivalently, only the horizontal component of the applied force does work. But the horizontal force equation already tells us that applied force times cosine 25 degrees equals the friction magnitude. Therefore, the applied work is plus Fk times the distance, or positive 1225 joules. The vertical component does no work, because there is no vertical displacement. The normal force and gravity are perpendicular to the horizontal displacement, so each does 0 work. The positive applied work exactly cancels the negative work of friction. The total work is 0 joules. We could also predict this answer from the work kinetic energy theorem. Net work equals the change in kinetic energy. Constant velocity means constant speed, so the kinetic energy does not change. The applied force does positive 1225 joules of work. Kinetic friction does negative 1225 joules. The total work is 0. The main lesson is that the work formulas become easy only after the forces are known. And constant velocity gives us 2 complementary facts. The forces balance, and the net work is 0.